So today we are going to talk about the law of conservation of energy, the law of conservation of mechanical energy. Okay, so we have studied this, that work done against any force gets stored, work done against a conservative force gets stored as what? The potential energy of a system. Okay, and work done on a system changes its kinetic energy, right? Okay, we'll talk about the conservative force only. But this thing is applicable to any force, that when you do some work, okay, let's suppose some work is done on an object, on an object. Okay, so let's suppose dw or delta w is the work done, and it is equal to, we can say, force multiplied by the displacement. Okay, work done on an object by force F. Okay, for small displacement dx, let's suppose F dot dx. Okay, let's call it dw for consistency. Okay, so dw equals to F dot dx. So now we know that this work done will change its kinetic energy. Okay, so this work changes its kinetic energy, right? So there will be some final kinetic energy and there will be some initial kinetic energy. So let's suppose the final kinetic energy is kf and the initial kinetic energy is ki. So we can say that this work done is equal to what? So this kf minus ki is equal to the work done. Okay, or work done is equal to change in kinetic energy. So this is equal to, we can say, F dot dx, right? So now let's suppose this force that is doing work, it is the conservative force. Okay, let's suppose this work is conservative force. So let's suppose that F is, let's suppose F is a conservative force, conservative force, right? So let's denote it by H suffix C, okay, to show that it's a conservative force. So now we know this thing, that work done against a conservative force gets stored as what? Potential energy of the system. Okay, so I can say work done against conservative force changes the potential energy, gets stored as potential energy of system, system or object or anything, right? So we can say that work done against the conservative force is minus of F suffix c dot dx. For small displacement dx, work done against the conservative force will be minus of fc dot dx. Okay, fc dot dx will be work done by the conservative force. We want work done against of it, so it is minus of fc dot dx. So this is equal to what? This is equal to final kinetic energy u suffix f minus the initial kinetic energy, right? So you have one relation. So fc dot dx is equal to what? Kf minus ki. Okay, so if you put kf minus ki over here, the change in kinetic energy over here, what do you get? So minus of sorry, kf minus ki is equal to uf minus ui. Okay, so if you absorb this negative sign, what will you get? Ki minus kf. Okay, so ki minus kf is equal to uf minus ui. And now move this ui on left hand side, kf on right hand side. So what do you get? So ui plus ki or ki plus ui is equal to uf plus kf. Okay, so the sum of potential energy and kinetic energy at initial location is equal to the sum of potential energy and kinetic energy at the final location. Okay, and this is what we call as the law of conservation of mechanical energy. So under the action of conservative force, the sum of potential energy and kinetic energy of a system remains conserved. So is this thing clear? For which force can you define the potential energy? For a conservative force, right? So potential energy can only be defined if the force involved is a conservative force. Force acting on object or a system is a conservative force. That means this will be applicable only when you are dealing with conservative forces. Okay, the force in the problem is a conservative force, and this will not be applicable if there are some non-conservative forces. Then you will have to consider the energy lost also. Is it clear? Okay, so this is not applicable when frictional force is there. Then we have to consider energy lost also. Okay, energy lost in friction. So you can say the initial potential plus kinetic energy is equal to final potential plus kinetic energy plus energy lost in friction. Energy lost due to the friction. Clear? Okay. So for now, let's forget about the friction and let's use this. Okay. Vertical circular motion. Vertical circular motion. So let's suppose a body is performing circular motion in vertical plane. Okay. So let's suppose there is a stone tied with a string and you whirl it in vertical circle. Okay. Or there is a bucket. There is some water in that bucket and you whirl it in vertical circle. Okay. Whatever. So whatever may be the object, you are moving that object in vertical circle. So for an example, let's suppose there is a stone which is tied to a string. So stone is at this topmost position. Okay. So there will be some tension in that string, right? So in what direction will that tension act? So let's suppose you are holding the stone over here, not the stone, you are holding the string. Okay, over here. So you are pulling the string downwards, right? So tension will act downwards. Okay, so when the stone is at the topmost position, tension will act downwards. What else acts downwards? The gravitational force, right? There will be gravitational force or weight of the stone acting downwards. Okay, so at the topmost position, the tension acts downwards, gravitational force acts downwards. Okay, and combined they provide the centripetal force. So when the stone is at this position, so let's call this topmost position as A and the position at bottom as B. Okay, so this point is A, this point is B. So now what will be the direction of tension? Tension will act upwards. Okay, so let's call this tension TA, T suffix A. Can you see this? And this one as T suffix B. Okay, and the gravitational force, it always acts downwards, right? So gravitational force always acts downwards. So now if we draw free body diagram, so if we consider the stone when it is at the topmost position, what are the forces acting on it? The tension and the gravitational force, both are acting downwards. Okay, so when the stone is at topmost position, topmost position, we can say that FCP at point A is equal to tension in the string at point A plus mg, right? and when the stone is at the bottom of the circle, is at the bottom of the circle. Okay, then what can you say? FCP at point B is TB. Okay, uh, yeah, TB minus mg, because centripetal force will act along the radius and towards the center. So, so what is so centripetal force here acts in upwards direction. So it is the total upward force minus total downward force, right? So we'll find the minimum speed such that this stone performs the circular motion. Okay, it completes the circular motion. It completes a revolution in a circle. So at the topmost position, I want minimum speed. So how much should be the tension? How much minimum value can be there for tension? The minimum value would be 0, right? Tension in the string, the minimum value for it will be 0. It cannot go negative. Can it go negative? So now FCP is the centripetal force, which we can write as mv square divided by r, and we want to find out speed at position A. So I will call it VA square. Okay, I will put suffix A, and I want this speed to be minimum. So I will make right hand side minimum. So mg cannot change, only tension can change. TA will be equal to 0. It cannot go negative, right? So TA is equal to 0. Okay, and therefore mva square upon r is equal to mg. So the weight is providing the required centripetal force here. Okay, tension is equal to 0. So m and m will get cancelled. So you get va square equals to rg, which implies va equals to what? Square root of rg. Okay, so speed at the topmost position will be square root of rg. So this is clear. Then let's suppose you move that stone such that the string becomes horizontal. Okay, such that the string becomes horizontal, right? So tension in the string will act in this direction. Okay, and the gravitational force now acts in this direction. Okay, this is suppose point C, and I want to find out speed at point C, the minimum speed at the point C. So what will I do? So here we can apply the law of conservation of energy. Okay, so here we can apply what? The law of conservation of energy. So see, we can say the sum of potential energy, which is gravitational potential energy, plus kinetic energy, okay, is constant. So initially the, the stone was at topmost position. Now you are revolving it in a vertical circle. So it goes from position A to position C. Okay, so how much is change in its height? So change in its height is this much, right? It is equal to radius of the circle. Okay, it is equal to radius of the circle, right? So you can say, using the law of conservation of energy, using conservation of energy, you can say potential energy at A plus kinetic energy at A is equal to potential energy at C plus kinetic energy, kinetic energy at C. Okay, which is mgh at point A plus kinetic energy is half of m into va square is equal to potential energy at C is mgh at point C plus kinetic energy is half of m into Vc square. Vc square. Okay. So we can cancel out m everywhere. M gets cancelled out, and then we can multiply this equation with 2. Okay, and I want to find out Vc, so I will move this term on left hand side. Okay, so first I will move the term and then I will multiply with 2. Okay, so I have G times HA minus G times HC. Okay, I am moving this term on left hand side, so it is equal to, okay, plus I have half of VA square, and this is equal to half of V suffix C square. Okay, then you can take G common, you can take G common and you can multiply with 2. So if I multiply with 2, I get 2 times G HA minus HC plus VA square is equal to VC square. Okay, and what is HA minus HC? So height of point A minus height of point C is equal to R, right? The difference between heights of points A and C is R. Okay, so you put that here, you get 2GR plus VA square. VA square is RG or GR. Okay, so GR is equal to VC square. So it is 2 times GR plus GR, that is 3 times GR. So VC is equal to what? VC is equal to square root of that. So VC is square root of 3GR. Okay, so minimum speed at the midway position. Midway position is when the string is horizontal, is square root of 3GR. Okay, and similarly we can do for this point, okay, the point at the bottom, and it will give us square root of 5GR. Okay, we have to do the similar thing. That means either take this point or this point. So sum of potential and kinetic energy at point A is equal to sum of potential and kinetic energy at point this B. Okay, and it will give us what? It will give us the speed at the bottom is equal to square root of 5GR. Right? The same procedure. Okay, so is it clear or do we need to solve it? So now let's find out difference in the tension in the string. Okay, sorry. So this thing must be clear that sum of potential and kinetic energies, it is constant, right? So see here, okay, check this equation, this equation. So speed is minimum or not? This equation is valid. Yes or no? Speed is minimum or not? The law of conservation of energy is valid. Okay, true that we are finding the minimum speed, and for that we considered minimum speed at point A and found I'm sorry, and found the minimum speed at point C and B. But speed is minimum or not, this equation is valid, right? That means speed is minimum or not, this equation is also valid. Okay, till this point, until we substitute VA square is equal to GR. Yes or no? Okay, so now, okay, good. So now, see, First of all, what we can do is at topmost position, we had written this, the tension in the string and the gravitational force, they provide the centripetal force, right? So FCP at point A is equal to what? Tension at point A plus mg, and that means tension at point A is equal to FCP at point A minus mg. Okay, so this is about point A. Then tension at this point, okay, we call this point point C. So tension at this point, it only provides the centripetal force because it is acting along the radius and towards the center. So tension at this point only provides the centripetal force. Okay, so T at C is equal to FCP at point C. Clear in this point? Okay, so then what I can do is I can subtract this. Let's call this equation 1, this one equation 2. Okay, so TC minus TA equals to FCP at point C minus FCP at point A. Okay, and if we subtract this minus mg, and that minus sign will become plus mg. Okay, and then we can substitute FCP at point C is what? M into Vc square upon R minus this is M into Va square divided by R plus mg, right? And M upon R we can take common, or let's take 1 upon R common only. Okay, so if I take 1 upon R common and multiply that with half, or multiply and divide by 2, what do I get? See, Tc minus Ta is equal to, I will say 1 upon 2R, okay, multiplied by, sorry, 2 upon R multiplied by half of M into Vc square minus half of M into Va square, okay, plus mg. And what will be this thing? So this is difference in kinetic energy. How much will be that? It is equal to difference in potential energy, right? The kinetic energy at C minus kinetic energy at A is equal to potential energy at the final point, this point. Final meaning second point. Potential energy at A minus kinetic energy at C. Yes or no? Okay, so this will be equal to, okay, this is equal to mgh, okay, mgh at A minus h at C. And what is the difference between heights of these 2 points? It is equal to R. Okay, it is equal to R. So it is equal to R. So this is 2 upon R multiplied by this mgr plus mg. So this upon R and R gets cancelled, and what do you get? You get 2mg plus mg, that is 3 times mg. So this is difference between tension of these 2 points. Tension at C and tension at A is 3 mg. Okay, good. So similarly, we can find out the difference between tensions at point C and this point B, okay, or difference between tensions at point A and B. Okay, so let's do that. So let's consider this point B. Okay, so here at point B, tension acts upwards, TB, and the weight acts downwards. Okay, mg is the weight which acts downwards. Okay, and then you can say the centripetal force at B is upwards, so which is total upward force minus total downwards force. So TB minus mg, the tension minus mg. Okay, so for point B, you can write that FCP at B is equal to TB minus mg. Okay, and move that mg on left hand side, so you get TB is equal to FCP plus mg, and what will be FCP? It is m into VB square upon R, okay, plus mg, right? And if you find TB minus TC, okay, TB minus TC, so using equation 2, you can say TC is equal to what? FCP at C. Okay, so what do you get? TB minus TC is equal to m into VB square upon R minus, okay, m into Vc square upon R plus mg. Okay, and once again we can do the same trick. So we can multiply by 2 and divide by 2. Half of m into Vb square will get minus half of m into Vc square. So change in potential energy. So plus mg. Okay, so this is 2 upon R, and this will be equal to what? Change in, so this is change in kinetic energy, which will be equal to the change in potential energy, which will be equal to what? Potential energy at C minus potential energy at B. Okay, so which is again how much? mgr. So which is again mgh at point C minus mgh at point B. Okay, so how much is height difference? R. So mgr is the change in potential energy, difference in potential energy. So you can put that, and if you put that, what do you get? Again this R and R gets cancelled. Okay, so 2 mg plus mg, that is 3 mg. This is TB minus TC. Okay, so the difference in tension at point A and C is 3 mg. Difference in tension between C and B is 3 mg. Okay, but what difference? So it is tension at B minus tension at C is 3 mg. Tension at C minus tension at A is 3 mg. So what will be tension at B minus tension at A? Tension at B minus tension at C is 3 mg. Tension at C minus tension at A is 3 mg. So tension at B minus tension at A will be what? It will be 6 mg, right? Okay. So I can say tension at B minus tension at A, therefore will be equal to 6 mg. This is clear, or is there a confusion? Then we'll do one more thing, and that is the spring block system. Okay, so let's talk about the spring block system. All right, so we have this rigid support, a spring, and a block is connected to that spring. Okay, and so this is rigid support. So this is the equilibrium position. That means when the block is at this position, there is no force acting on the block. Okay, it is not pulled. That means the spring is not stretched. The spring is not compressed. Okay, so let's call it 0. So when you stretch, when you pull the block, the spring will get stretched, and therefore some work will be done against the spring force. And we have studied about the spring force. What is spring force? So according to the Hooke's law, the spring force is equal to what? Minus of kx. Remember this? F suffix s is the spring force. It is equal to minus of k into x. That means if x is positive, the restoring force generated in spring, it will try to restore it back. So if x is towards right, the restoring force generated in the spring, it will be acting towards left. Yes, no? Okay, if you stretch the spring, spring will try to come back to its initial form. Okay, you stretch it or you compress it, it will try to come back to its initial form. So if you stretch it, the displacement will be positive, so force will be negative. Okay, if you compress it, the displacement will be negative. Okay, so force will be positive. Right, the spring force, the restoring force generated in the spring, always acts in opposite direction of the displacement. Right. Okay, so when you stretch this spring, you are doing some work against the spring force, which is a conservative force. Okay, so let's suppose you stretch it from position A to B. Okay, so suppose spring is stretched from position A to B. So from XA to XB, let's call it XA and XB. Okay, so the work done against the spring force will be what? Work done against spring force, which is F suffix s. It is equal to minus of Fs dot dx. This will be work done against the spring force for a small displacement. Okay, you want work done from XA to XB, so you have to integrate that. Okay, so work done from XA to XB, so you have to integrate this. So this integral from XA to XB of minus of Fs dot dx will give us that work done. Okay, and now we can put the value of spring force. This is equal to minus of integral from XA to XB. What is the spring force? It is minus kx, right? Minus kx dot dx. So minus minus sign becomes plus. K you can take out. Integral of x dx from xa to xb. Sorry. So this will be x square upon 2. Okay, x square upon 2, and then you substitute lower limit and the upper limit. So what do you get? You get k into xb square upon 2 minus k times xa square divided by 2. And because the spring force is a conservative force, okay, the work done does not depend on the path followed. Okay, work done does not depend where did you stop while displacing it from xa to xb. Okay, what stops did you take, or did you stretch it beyond that point and again you took it back to xb? It doesn't depend on all those things. It depends on only upon the initial and final position. Okay, as we can see, it only depends on xa and xb, initial and final positions. So spring force is a conservative force, and that's why the work done is equal to what? The change in potential energy of the spring. So this is equal to final potential energy of spring minus initial potential energy of spring. Okay, good. So this is equal to what? Final potential energy minus the initial potential energy. And then what we can do is we can consider that position A, okay, XA is equal to 0, okay, the initial position is 0, and XB is just equal to X. So what do we get? So we get potential energy at point X minus potential energy at 0 is equal to what? It is half of K into X square, because XB is equal to X minus 0, okay, or you can say you just get potential energy at X minus potential energy at X equal to 0. It's just half of K into X square. So we can only find out the change in potential energy and not the potential energy itself. So what do we do? For simplicity, we take the potential energy at X equal to 0, U of 0 equal to 0. Okay, so we define for simplicity that U of 0 is equal to 0, because we can only find the change. We cannot find what is the actual potential energy at any point. Okay, and therefore we get U at position X is equal to half of K times X square. So this is clear. The work done changes the potential energy of the system. Okay, so we can define a potential energy at some point. So that will be our reference. Okay, in reference to that we can find out potential energies at other points. So what is our reference? Potential energy at X equal to 0. We are taking reference as potential energy at X equal to 0 is equal to 0. Okay, so U of X is equal to half of K times X square. We get this simple relation. Okay, and then suppose the extreme position. So you stretch the spring. Okay, so extreme position is equal to, okay, A, right? So X is equal to A for extreme position. Okay, so that X is equal to 0 is known as mean position. X is equal to A is suppose the extreme position. Okay, so I can say the potential energy at X equal to 0 plus kinetic energy at X equal to 0 is equal to the potential energy at X equal to A plus kinetic energy at X equal to A. We can apply the law of conservation of energy, right? So the kinetic energy at extreme position, how much will be kinetic energy at extreme position? You stretch a spring, you release it from that point. How much would be the kinetic energy when you just release it? Must be 0, right? You stretch a spring, okay, that spring and block, you hold it and you release it. So when you just release it, there is spring force acting on it, but at the extreme position, that position, how much is its speed? It's 0. Then because of this spring force, it accelerates. Okay, it goes towards the mean position. But at the extreme position itself, how much is the speed? The speed is equal to 0, right? So the kinetic energy will be equal to 0. Got it or not? Everybody? Florence? Okay. So at extreme position, you are holding it. When you just release it, the kinetic energy will be equal to 0. Okay. And the potential energy at x equal to 0, we are defining it to be equal to 0, right? So now we can say kinetic energy at x equal to a is equal to 0, and potential energy at x equal to 0 is how much? It is 0. Okay, but uh yeah, okay. So what do I get from this? What do I get from this? So I get the potential energy at x equal to a is equal to kinetic energy at x equal to 0. Okay, so half of m into v0 square, you can say, is equal to, because potential energy is 0, so half of m into v0 square is equal to what? The kinetic, sorry, potential energy at a. Okay, how much is that? It will be half of k into a square. Okay, and from that, what can you find out? So v0 is equal to, this half and half will get cancelled out. So v0 will be equal to what? It will be equal to, take that m on the other side. Okay, so you get v0 square is equal to k upon m multiplied by a square, and if you take square root, v0 equals to square root of k upon m multiplied by a. Is it clear? Yes or no? Okay, we have just substituted the potential energy at x equal to 0 is 0, and what? The kinetic energy at x equal to a is equal to 0. Okay, and then we substitute potential energy at x equal to a, which is half of k into x square, and x is equal to a, that's why it is half of k into a square, and kinetic energy at x equal to 0 is half of m multiplied by v0 square, v0 meaning v at x equal to 0. Okay, and doing that, then half and half gets cancelled, take m on other side, so v0 square is equal to k upon m multiplied by a square, and therefore v0 equals to square root of that, so which is square root of k upon m multiplied by this a. Okay, square root of a square is a. Clear? We can also find out speed of the spring block system at any position, and for that, what do we need to do? So we just have to consider, okay, u at x plus kinetic energy at x is equal to u at a plus kinetic energy at a, and kinetic energy at a is equal to 0, kinetic energy at extreme position is equal to 0. Okay, substituting that, you get kinetic energy at x is equal to u at a, potential energy at a, minus potential energy at x. So from this, half of m into vx square, okay, or let us just call it v at any position x, let's just call it v. So it is equal to, potential energy at a is half of k multiplied by a square, minus potential energy at x is half of k multiplied by x square. So this half get cancelled out throughout. Okay, so you get v square is equal to k upon m multiplied by a square minus x square, right? I took k common, so on this side you get a square minus x square. Okay, and take m on other side, so you get k upon m multiplied by a square minus x square, and therefore v will be equal to square root of this thing, square root of, okay, k upon m a square minus x square. right? Right. And then you can find out kinetic energy at any position. So just take half of m multiplied by v square. So it will be equal to what? Half of k multiplied by a square minus x square, right? Kinetic energy at any position x is equal to half of k, okay? K is spring constant. Half k you take common, a square minus x square, okay? And you add potential energy and kinetic energy. So u at x plus kinetic energy at x will be equal to what? So it is half of k into x square plus half of k multiplied by a square minus half of k multiplied by x square. It is this term, okay? So this half of k into x square and minus half of k into x square gets cancelled. So you get sum of potential plus kinetic energy is half of k into a square for a spring, okay? You get this thing, this formula. So if I want to show it on a graph, how will it look like? So if I want to plot the energy on the vertical axis, okay, so what will be total energy? Total energy will look like this. Total energy will look like this, okay? So this is x equal to 0, right? This is x equal to 0. So this is suppose plus a, this is minus a, this is plus a, okay? So this is valid from minus a to plus a, from negative extreme position to positive extreme position, okay? Then the potential energy will look like this. It is half of k into x square. So it is just a parabola, x square, right? So as x increases, the potential energy increases. So how much will be its maximum value? Let's draw it with this color, like this. This is what? This is the potential energy. This is the potential energy. And what is kinetic energy? So it is total energy. This total energy, okay, this total energy minus potential energy. So that graph will look like this, okay? It will look like this. So this is kinetic energy, right? This curve is a kinetic energy, this curve is a potential energy, and you add both, so you get this total energy, okay? Let us see some problems. So what is the minimum velocity with which a body of mass m must enter a vertical loop of radius r so that it can complete the loop? This is very straightforward. Tell me the answer. What is the minimum velocity with which a body enters a vertical loop? So where is the minimum velocity? At which point? This point, this point, this point? At the topmost point, right? How much is that? Square root of gr. We solved it, no? Okay. So answer is square root of gr. Yes or no? Okay, this is a direct question, a straightforward direct question, right? Let's see the next one. A mass m is attached to a thin wire and whirled in a vertical circle. The wire is most likely to break when the option A, inclined at an angle of 60 degree from vertical, the mass is at the highest point, the wire is horizontal, the mass is at the lowest point. Tell me, where is the tension maximum? when mass is at the lowest point. So where will the string break? When mass is at lowest point, right? Okay, so the string will break, right? The wire will break when the tension is maximum. Tension exceeds the value, okay, which which the wire can sustain, right? It will break at that point. So when the mass is at lowest point, it will break. Most likely, okay, it is most likely to break when the mass is at lowest point. Again, this was also straightforward, right? Is there a question? Is there a doubt in this? Okay. The next one, a body initially at rest and sliding along frictionless track from a height h, as shown in the figure, just completes a vertical circle of diameter AB equals to D. So this is the body. It is sliding from this point and it completes vertical circle of diameter AB equals to D. The height h is equal to. So what should we do? We want to find this height in terms of D. What should we do? So this is simple. See, in order to complete this vertical circle, okay, in order to complete this vertical circle, it must enter this loop with minimum velocity which is required to complete the vertical circular motion, right? But it is entering at this point, it is entering at bottom. So how much is the minimum velocity at bottom? The square root of 5 gr. So it must enter this bottom point with this velocity, square root of 5 gr, right? Okay. Then it is very simple. The potential energy at this point gets converted to kinetic energy at this point. Okay, so potential energy at top, I can say at top, let's suppose it has only potential energy, and at the bottom, at this point, it has only kinetic energy. So potential energy at top, or we can say sum of potential energy. Let's call this point C. So potential energy at C, okay, U at C plus kinetic energy at C is equal to U at A plus kinetic energy at A. So it is released from this point. So it has no kinetic energy. This is 0. Okay, Kc is equal to 0 because it is just released. Then you can take UA on left hand side, potential energy at A at left hand side. Okay, so what do you get? Kinetic energy at A is U at C minus U at A, which is mg h at C minus h at A. So which is height difference between these 2 points, and which is equal to what? H. So this is equal to mgh. Okay, and kinetic energy at A is half of m into Va square. So this is equal to mgh. So m and m gets cancelled. And how much is the kinetic energy? So it is, sorry, how much is the velocity? Square root of 5 gr. So its square is 5 gr. Okay, so which implies that 5 gr upon 2 is equal to g times h. So g and g also gets cancelled. So you get 5r upon 2 is equal to h, and you can multiply and divide by 2 because you want h in terms of d. So if you multiply and divide by 2, what do you get? So H is equal to 5 times 2r upon 2, or 2 times 2, right? You are multiplying and dividing by 2. So 2r is d, okay? So you get 5d upon 4. This is the answer, right? Okay, but when in exam, don't do all of this, right? In exam, you will just say potential energy here gets converted to kinetic energy here. Okay, so mgh is equal to half of m into va square, and va equals to square root of 5 gr. Cancelled. Okay, gg cancelled there itself, right? You don't have time to do this, all of this. Yes, no. Okay, right. So this was also a simple problem. Let's see this one. As shown in the figure, a mass is performing vertical circular motion. The average velocity of particle is increased. Then at which point will the string break? Repeated question. Okay, answer is option B, right? So when was the earlier? Okay, that was earlier. 2019 it got repeated. Okay, next question. A child is sitting on a swing. Its minimum and maximum heights from ground are these: 0.75 meters and 2 meters respectively. Its maximum speed will be. So this is simple. Okay. So its maximum speed will be how much? So you can say half of m into v square, whatever is its speed, maximum speed, it's equal to mg, the difference between heights at these 2 points. So let's call this one A, this one B. Okay, so mg hb minus mg ha. Okay, and you can take mg common, so it is hb minus ha, right? Understood or not? Okay, so then m will get cancelled, take 2 on other side, so v square is equal to 2g multiplied by hb minus ha. So how much is hb? 2 minus ha 0.75, and then this will be 1.25, right? 1.25 times 2, 2 times 10 multiplied by 1.25. So 1.25 times 2, 2.5, 2.5 times 10, 25, and it is v square. So v is equal to 5 meters per second. 5 meters per second is the answer. Option B. A stone is tied to a string of length L and is whirled in a vertical circle with the other end of the string as the center. It will be at the center. At a certain instant of time, the stone is at its lowest position and has speed u. Okay, so at lowest position, the speed is u, right? So at lowest position here, okay, the speed is u. Then the magnitude of change in velocity, the magnitude of change in velocity as it reaches a position where the string is horizontal. Okay, that is here, right? G being the acceleration due to gravity is. All right. So this is little bit tricky question compared to the all the previous questions. Okay. So they are asking what is magnitude of change in velocity. So velocity at this point is directed like this. Let's call it u bar. Okay, it will have some magnitude. Velocity at this point. Okay, let's suppose it is moving like this. It is moving like this. So at this point, it will be directed like this. It will have some magnitude, right? It will have some magnitude. So let's call this magnitude as v. Okay, so what is change in velocity? Let's call this one u bar and this one as v bar. So what is change in velocity? So for that, this is your initial vector u bar and this is the final vector. Okay, and you want to subtract this one. This is v bar, this is u bar. You want to subtract this one from this one. So you can draw its negative vector, right? You can draw its negative vector, which will be directed like this, let's say. Okay, so this is minus v bar, and then you can add them. This is minus v bar, and then you can add them. So u bar plus minus v bar, okay, will give you this vector. And they are asking what is the magnitude of change in velocity. Okay, so you can find change in velocity and you want magnitude of that. So you want magnitude of this vector. Okay, so this is u bar minus v bar, sorry, minus v bar, but you don't want, I mean, you want magnitude of this. So how much would be the magnitude? It will be u square plus v square, right? Use the triangle law. Magnitude of this vector will be what? Sorry, square of magnitude will be u square plus v square. Yes or no? Yes, Tamil Selvi, understood or not? Okay, good. So square of magnitude of this vector, you want change in velocity, magnitude of change in velocity. So you can say u bar minus v bar, magnitude of that square, is equal to u square plus v square. So this is u, that you know, but how much is magnitude of v? That we can find out. Okay, that we can find out. How come? So using the law of conservation of energy, right? So this much height, okay, this much height is equal to what? Length of string. Okay, so when the string goes from here to here, okay, so some of its potential energy gets converted to what? Kinetic energy, right? So potential energy plus kinetic energy at this position is equal to kinetic energy at this position. Okay, so we can say that half of m into u square is equal to half of m into v square, okay, that is at this position, plus mgh, okay, that is mgl. Can we say this? See, when, let's suppose there is this stone, okay, it goes from this height to this height, it loses its potential energy and part of that potential energy gets converted to kinetic energy. So let's suppose it has zero potential energy at this point. Okay, let's suppose it has zero potential energy at this point. Okay, so its kinetic energy at this point is equal to what? Sum of potential energy and kinetic energy at this point, right? So I can say half of m into u square is equal to half of m into v square plus mgl, right? Okay, so then gets cancelled, m gets cancelled, and you want v square. Okay, you want v square. So take that gl on other side or multiply whole equation with 2. So what do you get? You get u square equals to v square plus 2gl, and that means v square is equal to u square minus 2gl. Okay, v square is u square minus 2gl, and put that here, right? Okay, so v square is u square minus 2gl. Let's put that here. So you get, okay, whatever is change in magnitude square, that is equal to, this thing is equal to what? U square plus u square minus 2gl. So I have substituted in place of v square u square minus 2gl. Okay, then u square plus u square will give you what? 2u square. Okay, 2u square minus 2gl. Then you can take 2 common, and you want only magnitude, not magnitude square. Okay, this is change in velocities, magnitude square. You want only the magnitude of u bar minus v bar. U bar minus v bar. So it will be square root of right hand side. So square root of 2u square minus 2gl, or you can take 2 common, u square minus gl. So this is the answer. Okay, so this is the answer. Option A is the answer. Is it clear?